Hi everyone, this is Dan Barry in Silver Spring. It's about 1 o'clock, so we're going to get going with the webinar. This month's webinar is titled Understanding and Monitoring Drought. We have 4 speakers today. We're going to hear from Chris Hain from NOAA NSDS, Krista Peters-Ledard from NASA Goddard, Amir Agakuchik from University of California at Irvine, and Andy Wood from the NOAA Northwest River Forecast Center. These 4 individuals participate in a task force that's been organized by the MAPP program, the Drought Task Force. There are about 30 MAPP-funded investigators who participate in this task force, and they're focused on drought monitoring, understanding, prediction, and it includes individuals from academia, the federal agencies, and laboratories. They're involved in a number of activities, including preparing a special collection of papers for a journal of hydrometeorology, special collection titled Advances in Drought Monitoring and Prediction. We're expecting something like 20 papers to go into that from the task force. And they also organized a fall meeting session at the AGU annual meeting, which was titled Advancing Drought Monitoring and Prediction with Applications to Decision Making. We also hosted a meeting in Fort Collins, Colorado last fall. 2 individuals today, Krista Peters-Ledard and Andy Wood, are co-chairs of this group. So we're going to hear a nice, diverse series of presentations today on the topic of understanding and monitoring drought. And our first speaker is Chris Hain. So Chris, are you on the line?
Yes.
Great. I'm going to pass control over to your computer.
All right.
All right, great. Whenever you're ready, take it away, Chris.
All right, great. Thanks, Dan. Thanks for the invitation to talk today. The title of the talk I'll give today is Development of a Thermal Infrared-Based Framework for Mapping Drought, and just kind of walk through some of our regional applications and then kind of chart out the path towards a global scale implementation. On the screen, you'll see a lot of collaborators for this project: Martha Anderson at USDA, Jerry Zahn and Lee Fang here at NOAA NSDS, and then Mark Svoboda and Brian Wardlow at the Drought Mitigation Center. So our main tool that we use to monitor drought is the ALEXI Evaporative Stress Index. As you see here on this water balance approach part of the slide is kind of how this is more of a land surface modeling water balance approach where you need to know things like soil hydrological parameters, holding capacities, evaporation and stress parameters, and mainly the model is driven by incoming precipitation and then meteorological inputs. So you need to know a lot of things to kind of try to model the land surface, where with ALEXI, a 2-source energy balance model, we kind of look at it from a diagnostic standpoint instead of a prognostic standpoint, where we use mainly changes in land surface temperature from geostationary sensors, and then given the known radiative inputs, we can calculate the water loss required to keep the soil and vegetation at the observed temperatures. So what's nice is that these 2 methodologies kind of get at the same problem, yet they tend to be independent because from the LST standpoint, we don't need precipitation, and then from the land surface modeling standpoint, you mainly use precipitation to drive the model. Just kind of walking through, ALEXI ESI represents temporal anomalies in the ratio of actual to potential ET. So, like I said, it does not require precipitation data. The current surface soil moisture state is directly deduced from the changes in morning land surface temperature. So this, in theory, would make a method like this a little bit more robust in areas where you don't have good ground-based precipitation monitoring, data-sparse regions. But we have shown that it's also a very good tool over the United States when you do have good precipitation monitoring. Another added benefit is that the signatures of vegetation stress that we see in the LST signal really show up before you have any deterioration of the actual vegetation cover, compared to something like NDVI, where you actually need to see actual damage to the vegetation before you can actually see a drought signal. Using the land surface temperature like we do in ALEXI, we can start to see stress in the vegetation where the plant may start to regulate its water use, and which leads to elevated canopy temperatures and kind of an early warning metric that you're seeing stress in the vegetation before you actually see any damage. So Also, ALEXI, by the nature of itself, it includes certain non-precipitation related moisture inputs, irrigation, vegetation rooted to groundwater, lateral flows, things that we don't need to model that are inherently within the land surface temperature signal. And then these are things that need to be modeled a priori in prognostic land surface models. So ALEXI also provides a check on some of these non-precipitation inputs. And then ALEXI also provides an independent assessment of current drought conditions, supplementing both precipitation and modeling-based indices. And it's an invaluable resource to decision makers who kind of depend on this convergence of information in the decision-making process. So just at the bottom there, you see kind of the inputs we use in our North American and CONUS ESI products. Mainly, we get our land surface temperature from geostationary data, and a lot of our vegetation parameters come from MODIS. And then meteorological data can come from things like GEOS5 and MIRA or the North American Regional Reanalysis, just depending on where we actually run the model. This is kind of a busy chart. This is taking our CONUS ESI and comparing to a number of both remote sensing indicators here at the top. ESI 1, 2, and 3 are just the length of the compositing window. This ETI is a ET only metric, and then the VHI is another mainly temperature and NDVI sense method that is developed here also at NESDIS. And then on the left here are the precipitation based indicators, and a lot of these are both ET from the 3 land surface models in NLDAS, Mosaic, NOAA, and VIC, and the ensemble average, and then the soil moisture. So kind of looking at this first plot here, then these are all compared to anomalies in the drought monitor classifications. So as you see, like the ESI 1, 2, and 3, for all the remote sensing indicators, shows the highest correlations with the drought monitor. So that was a really important finding, and this kind of highlights this ability that, you know, looking at the land surface temperature is maybe a little bit better than looking at just degradation in vegetation, which is something like the Vegetation Health Index relies on. And then also kind of showing that the ESI signal really is tied to the soil moisture dynamics. We have really strong relationships and high correlations between all ESI at 1, 2, and 3 months with all of the land surface models in NLDAS, and then, you know, the highest correlations actually occur with the ensemble average. And this is kind of what I was talking about before. This is from this year, 2012, and looking at these changes in ESI, this early warning tool. And on the left here, you'll see these are the monthly changes in ESI, and then the monthly change in the U.S. Drought Monitor classifications. And what was really interesting that we saw in our signal this year is during the late April and early May period is we started to see a real strong change in our ESI signal from pretty positive values to pretty strong negative values by the end of May. But it was this change metrics that we were looking at that really started to highlight that, you know, something was going on across a lot of the Midwest, and there was, you know, a certain amount of vegetation stress that we were seeing in our signal. And if you look here in May, you know, our monthly change was a lot stronger and had a lot larger aerial coverage over the central United States than what we saw in the drought monitor. And, you know, this change here in May was more consistent with what the drought monitor change looked like in June. So, you know, this flash drought scenario where you have these really fast developing stress and fast developing drought areas, it's something where the ESI is really able to pick up on, and this was kind of the year where, you know, with such a fast developing drought and such a large aerial drought, was really able to show the benefit. This is just kind of a different way of looking at these changes in ESI. So this is a climate division in northwest Arkansas. So what you have here is your month March through October, and then the drought monitor's actual classifications. And then this column here is the actual ESI value. So the ESI, you know, when the ESI started getting the negatives, pretty coincident with when the drought monitor started introducing classifications for this region. But if you look at this change in ESI over 2-week periods, you start to see that in early May and late April, in these 1- and 2-week composites, we started to see a rapid degradation in the ESI signal. And so this is something we're looking at and finding ways to try to develop both from an automated standpoint and a way of communicating these changes to allow a forecaster maybe look at an area and say, the ESI signal is degrading, if you had continued dry and warm conditions, the chances of a drought developing, it might give you a little bit of a lead time. So one thing that we've done is, up until now, we had only run our algorithm over the CONUS, the continental United States. So this year, we've expanded to North American domain. It goes from about 5 degrees north to about 60 degrees north. It's run at 12 kilometers, slightly coarser than the CONUS, which is run at 10 kilometers. But this is just two examples from the two past years in July 2011 and 2012. Both pretty significant droughts in these years. And as you see here on the left, the actual North American Drought Monitor for July 2011, and then our ESI composite for 2011. You get good relative agreement for the Texas and Mexico drought of 2011. And then 2012, you get good agreement from the western and central U.S. drought over the CONUS. So at this point, this is a product we'll start to roll out this warm season, producing both the CONUS ESI maps and then these North American ESI maps to support the North American Drought Monitor. So the next thing I want to kind of talk about is how do we use this ESI information or this ALEXI information in being able to assimilate it in this kind of the soil moisture signal into land service models. So kind of some of the work we've done is kind of showing the synergy of thermal IR and microwave methods for monitoring soil moisture. These top two maps here on the left is the ALEXI NOAA. These are time series anomalies correlations over our climatology, which runs from 2000 to 2012, and then the same period, 2002 to 2011 for LPRM using AMSR-E. So as you see, for the most part, over the central United States, both microwave and thermal give pretty robust signals as compared to using NOAA as a reference. One of the real strong benefits of a thermal IR method is getting this discernible soil moisture signal from areas of pretty much moderate to dense vegetation, especially here over the southeast, in areas where you don't get as much useful signal with microwave signals. And this is kind of highlighted here when you look at these anomaly correlations and kind of bin them as an average April to October fraction cover. And as you see and this is kind of the difference between ALEXI and then the AMSR-E or LPRM method. So over low to moderate vegetation, in general, the LPRM NOAA relationships are stronger, but as you get above 60% vegetation cover, you start to see it go the other way. So, what we've kind of shown is that using both thermal IR methods and microwave methods, you get a more complete picture over a varying amount of vegetation cover. And we've used this information to assimilate these our soil moisture proxy from thermal IR and then the surface soil moisture retrievals from microwave sensors. And we've assimilated them using an ensemble common filter and lists. And these simulations use NOAA 2.7. But you see, for the most part, you can see these lines. The LPRM, you tend to. So this was a data denial study where we had a control run forced with high quality precipitation and then an open loop forced with satellite. And the goal was to see how much of the random errors in the satellite-based precipitation that these two soil moisture retrievals could correct. And generally what we found is, there is a potential to correct, these random errors in these satellite-based precipitation data sets. And for the most part, LPRM corrected more in the surface and ALEXI corrected more in the root zone. So, like I said, having an ability to kind of get this root zone signal from ALEXI over moderate to dense vegetation kind of supplements, higher quality surface signal that we get from microwave. All right, and so this kind of brings us to another thing we'll be kind of rolling out this warm season in kind of a test mode is this data assimilation system we've been developing that will assimilate both ALEXI and microwave. And as you see there, we're still working on what microwave data sets to use. AMSR2, WinSat, and SMOS are what we have available. And then also ingesting some of these real-time fraction cover, albedo, emissivity, some of these other MODIS vegetation-related data sets into LIS using NOAA version 3.2. Our study domain will be CONUS and run at 10 kilometers, study period from 2000 to current. We're developing the climatology now, and in this summer we're kind of running this in like a real-time internal test mode once a week to produce assimilated drought anomalies from NOAA, assimilating both this LPR, not the LPRM, but the new microwave data sets, and then this ALEXI one. And then hopefully, given how well it performs this summer, we'll, with the goal of producing these weekly real-time drought products in the 2014 warm season. Just quickly go through a couple future data sets that we're hopefully going to be rolling out in either a test mode this warm season or in 2014. Now that we've moved to North America with the ESI at 12 kilometers, we are working on producing our ESI over the CONUS at 4 kilometers. Currently it's at 10 kilometers, so using the full resolution imager data and getting down to 4 kilometers. And this is a couple examples of irrigated areas where when you saw in the 10-kilometer land surface temperature signal, you get kind of this blocky, and you don't represent some of the areas of irrigation well compared to what our future 4-kilometer both ET and ESI will produce. So this is something that we'll hopefully be rolling out in a test mode this year and hopefully producing in real time in 2014. And then another thing we've been working on is taking what we've done over North America in the CONUS and applying this globally. The first version of this will be a half degree. This is more of a retrospective study, but in the future when these real-time global land surface temperature data sets from geostationary sensors become available, we'll be able to hopefully produce these ET and ESI maps at 10 kilometers in the future. So that kind of wraps up what we're working on. I kind of wanted to give a kind of an overview of all the things we're doing and how they all tie in. And, you know, some of these higher resolution and global data sets will eventually feed back into our data assimilation type systems. So it's kind of where we're at now. And so I'll let any questions and I'll be happy to answer.
Chris, that was great. Thanks so much. Are there any questions from anybody in the room for Chris?
Chris, this is Krista. I have a question.
Yes.
For your 3 potential soil moisture products, what retrieval algorithms will you be using? You had WinSat,
yeah,
Answer 2.
That's something Jerry here, Jiwoo, was working on that, and you know, I think at this point I think their idea is to use the LPRM. Now, they're doing 2 things. They're doing the LPRM, and then I believe they're using the LPRM optical depth, and then they use that in the single channel retrieval. So that's something I'll have to touch base with him on, and we can get back to you.
Okay. Thanks.
Chris, this is Jerry. This is Jiwoo. Yeah, indeed, we are trying to combine the LPRM and the single channel retrieval. So hopefully we can get a better product.
Are there any questions on the phone line for Chris?
Yeah, this is Pedro Restrepo from NTRFC. Chris, very interesting presentation. I was wondering if you could give me a copy of the presentation for me to show to the people here in the office.
Yeah, all these presentations are going to be up on the MAPP website, so you can visit that, you know, after the webinar is over and download the slides. They're actually already up if you'd like, and the link is in the email that I sent earlier today.
Oh, great.
And Dan, can I send you an updated, because it's slightly different noise I sent you last night.
Yeah, sure, absolutely.
Right. This is John from Delaware. I have a quick question.
Yeah.
How does the ALEXI run if it's based on the thermal for areas that are covered by clouds in a large part of the wet season?
Well, yeah, that's obviously we have a cloud cover constraint, so that's why we kind of use these 1, 2, 3 month composites for the ESI. But you know, as you saw in some of the North American plots over Canada, you do get a lot more cloud cover than you do over Mexico and the United States, and you know that's something where we try to do a really good job with our cloud clearing when you only have maybe a retrieval once every 7 or 10 days. But obviously, you know, our signal to noise is a little bit different than what we deal with over, you know, areas that may not be as cloudy. But as we move globally, we're going to be dealing with some of these other, you know, these issues, especially over the Amazon and some of the monsoonal regions of Asia. So it's something we're working on, but, you know, we're always going to be limited by clouds.
Sure. Okay.
Great. We have time for one more question. Anybody else on the phone line or in the room? No? Okay. Well, our next speaker, thanks a lot, Chris. Our next speaker is Krista Peters-Ledard from NASA Goddard. Krista, are you on the phone? Let's see, she's muted. There we go. Krista, are you there?
Yes, I'm here.
Okay, great. I'm going to try switching control over to your computer.
Okay. I'm sharing my desktop.
Great.
And
nice background.
Now you should see my slides.
All right, great. Whenever you're ready, go ahead.
Great. Okay, thanks. Following nicely on Chris's talk, my talk is about some data assimilation experiments that we've been conducting to advance the North American NLDAS, and particularly with a focus on drought monitoring. I'd like to acknowledge my co-authors, David Mako, who's on the line, Sujay Kumar, also at Goddard, and Yulong Xia and Mike Eck at INSEP. So 3 pieces to the talk here. The first is just a little bit of background about how the NLDAS drought monitor works today. And as Dan mentioned, we have our drought task force, and I'm going to just review the 3 case studies that we've been focusing on. Then I'm going to show some examples from soil moisture assimilation, first evaluating against in situ data and stream flow, and then impacts on drought metrics or indicators, and then snow assimilation and impact of that. So this is the first of our 3 case studies that we identified in the drought task force. The first one was in the western U.S. The duration was actually much longer than this July 2002 period that I'm showing. It roughly corresponded to 98 through 2004. And shown is the drought monitor at the top, along with 2 examples from the NLDAS drought monitor. These are just 2 models, the Mosaic model on the left and the NOAA model on the right. And just to give you a sense for how these models produce soil moisture percentiles that correspond roughly to the drought monitor. In this example, the drought monitor was not using the NLDAS drought soil moisture percentiles. In later examples, these soil moisture percentiles have been provided as inputs to the drought monitor. So you would expect the correspondence to be better. Okay, so the next slide is August 2007. This is another one of our droughts. This is the southeastern U.S. drought in 2007. You can see very clearly in Alabama and Georgia, especially. And then you can see the 2 corresponding images from the NLDAS drought monitor, just showing where we had success and maybe not as much success in indicating the drought. But I think overall, things look pretty good. Okay, then finally, the most recent Tex-Mex drought. This is an example from the August 2011 time period. For this example, the drought monitor is in the upper right corner, and what's shown in the large upper left is the ensemble mean from all of the NLDAS models used in the drought monitor. And in this example, it's Mosaic, NOAA, SAC, and Princeton's VIC model, Princeton and University of Washington. You know, overall, the models look pretty good. Now in this time period, they were used as input for the drought monitor, so it's a little bit of a, you know, I guess cyclic. But what I want to point out is that when we're talking about data assimilation for drought monitoring, it's particularly difficult to show benefit over and above the NLDAS itself. You know, NLDAS has already shown benefit for drought monitoring. So what we're really asking is, does the assimilation of data help us either in detecting the onset of the drought, and that's related to some of the things Chris was showing. Perhaps there's information there that is not available in the initial NLDAS runs. Another example is for recovery. Does it help you with recovery assessment? And also, you know, just in general, does it help you detect the intensity, duration, and severity? So now we're going to move on to the second part, which is the soil moisture data assimilation. So for this example, we're running the NLDAS domain, and if you're not familiar with NLDAS, I guess you can see my mouse, correct?
Yeah, that's right, Krista.
Okay. So the domain for the NLDAS, as you've seen, is CONUS, you know, as shown in the previous images. It's a 1/4 degree resolution. We're going to be running for a period from 1979 to 2012. And we're using the NLDAS Phase 2 forcings with the NOAA 3.3 LSM using the LIST model, which is also what Chris used. The data assimilation for this is actually a soil moisture data set that combines multiple sources. It's produced by ESA, and it's called the Essential Climate Variables Soil Moisture data set. In the recent period, up until AMSRE stopped working at near the end of 2011, that data set consisted heavily of the AMSRE LPRM algorithm that you heard discussed earlier. More recently, it would be weighted more towards ASCAT or, and eventually, I guess, SMOS, but not yet. In the previous periods, there's data from SSMI and SIMR. When we assimilate the data, we use flags that, this gets at a point I think Chris also made, is that there's certain times when the remotely sensed soil moisture does not give you good information, and one of those times is when you have light to moderate vegetation cover. So this is another example of where our work would favor assimilation where there's low vegetation, you know, and if there's heavy vegetation, you would just use what the NLDAS models only give you. There's also flags for other things like snow cover, frozen ground, and radio frequency interference. We use a standard technique for scaling the observations, which is just CDF matching. So you run a climatology in the open loop and you scale the observations to the model. We use a 12-member ensemble and some standard error characterization. So to evaluate this, we use a suite of data that we've been provided from SCAN, which is a special quality controlled subset of SCAN that Rolf Reichle and his group have developed here at Goddard. There's also ARS experimental watersheds. Mike Kosh has provided us the data from these. We use streamflow gauging data from the USGS. And for the snow comparisons you're going to see a little bit later, we use the Global Historical Climate Network, and we also, as a reference, compare to the CMC analysis. And just as a point, we use something called the Land Verification Toolkit, LVT, and that's now open source. If you're interested, contact me afterwards. Okay, so this is just to show you where we've done our evaluations on the soil moisture, and each of these tables provides some metrics on the impact of soil moisture assimilation between the open loop. So the first column means there's no data assimilation. This would be essentially an NLDAS run without assimilation. And then with the data assimilation is provided in the rightmost column. So you have anomaly correlation, which is our standard metric, just showing that there is a statistically significant improvement. But as I noted, NLDAS is already pretty good to begin with. I mean, an anomaly correlation of 0.74 is quite high. So it's hard to beat. And I'm going to show you more evidence later that we do see an impact. Against the SCAN data, we have in the open loop a 0.6 anomaly correlation, and that increases to 0.7 after the assimilation. So that's a very encouraging result. For the root zone, which is the lowest, you see a slight increase, but it is barely, it's not even, I guess, technically statistically significant. So, we saw this and we were like, okay, well, that's potentially encouraging, but not a slam dunk. So let's look at some other metrics, or let's look at some other ways to assess the improvement. And the next slide, I think, is a more convincing demonstration. This is basically an evaluation of stream flow with and without data assimilation. So the black bars are going to be without assimilation, the open loop, and the red bars are going to be with assimilation. And this is divided into different basins. These basins are actually based on 961 unregulated basins that are similar to the evaluation of NLDAS that was just published recently. And so basically you pick these unregulated basins out and you route the stream flow produced by the NLDAS models to the outlet, and then you can get a modeled stream flow that you can compare directly to the observed stream flow. And then you can aggregate the statistics up by these water resource regions, and that's what each of these bars is. If you want to look at a summary just across all regions, you can see the open loop RMS error at the bottom and the bias, and you can see that for both cases, the RMS error is reduced and the bias is also reduced. So we're pretty convinced that there's value to the soil moisture assimilation, and it's mostly across the board, which is also, nice to see. So now we can move on to looking at the drought metrics. So the first thing we did was just to show you visually what the open loop or no data assimilation looks like for our 3 case study periods, and what the with assimilation results look like. And the first thing you'll see is when you look at that is that they're not dramatically different. You can see some areas of difference, but they're quite subtle. Now that's sort of by design. That's the way the CDF matching approach is intended to work. So now we start to say, well, how can we assess the impact of this relative in a more quantitative way? And so the next slide shows you our first attempt at that. So what you're seeing on this slide is a time series from 2000 to 2012 of the drought monitor area in a given drought category. So if you're familiar with the drought monitor, and I should have pointed this out earlier, there's categories D0 to D4, where D4 is the most significant drought, and the D0 is just sort of starting to show drought. And so the blue lines are the drought monitor area percentages for the south. So that's all the green colored states in the upper right corner. And so the first thing you notice, by the way, the other 2 lines, the black line would be the open loop run, which is NLDAS without assimilation, and the red line is with assimilation. So the first thing you notice is that the correlation between these is quite significant, which is expected and good, and that's one reason why this is used as part of the information behind the drought monitor. But also what you start to see is that there are certain times and periods where you can see that the data assimilation makes a difference. In certain cases, and let's pick one here, which is a good case, right? So if you look back in the 2003 period, you can see that we were tending to push the drought in the right direction here. In the most recent severe drought, we're actually tending to push in the wrong direction. So we, at least relative to the overall drought monitor, although we have to be careful. We are determining drought area solely by our thresholds on soil moisture percentiles, whereas obviously the drought monitor uses a lot of additional information. So it's not exactly a fair comparison, but I think it's giving us some insight into, at what severities and at what times the soil moisture information does appear to change the area that we might consider to be in a given drought category. So that's, there's a lot of information here, and because of the time, we can't go into all the details, but I just want to show you one other example, and this is for the Southeast U.S. Okay, so remember in the Southeast U.S., the main drought we were talking about was in the 2007 period, right? So interestingly, in the 2007 period, we were sort of asking, well, does it help with onset? If you look at the different categories here, and if you remember, the Southeast U.S. from Chris's map is one of those areas where in parts of the area are heavily vegetated, so you don't get a lot of benefit from AMSR-E in this area. Although there does seem to be something about the recovery where there seems to be a benefit, and so we're going to look into that more. You can see as it's recovering in the latter part of 2007 into 2008 that there appears to be, some suggestion that the assimilation's moving it in the right direction. So we're going to keep looking at this, but I think overall, there's different locations. I mean, here's another example in 2002 where, things definitely are moving in the right direction. So we've got to study this more, understand when and where it's helping and why, but there is potential for, I guess, helping monitor drought using these assimilated products. So let me move on to this next topic in the interest of time. So snow data assimilation. So in the snow assimilation world, we don't have a continuous data record that spans the entire period like that ECV soil moisture product did. So we sort of had to create our own, and we have 3 different data records. There's the SIMR from 78 to 87, the SSMI from 87 to 2002, and then AMSR-E. So we've developed retrievals based on the Chang algorithm for simmer and SSMI, and then there's a standard set of AMSRE retrievals from Kelly et al. But the most important thing that we do, which is different from what we do for soil moisture, is that we bias correct these retrievals, and we're going to talk about that in a minute. So, so when we assimilate these variables, we use a suite of data using a Cressman analysis to grid the data on the HCN data, so that we do remove some of the bias. So in this example where we compare, in this case we're comparing just with and without the data assimilation, and we compare to the CMC as a reference. So let's look down here at this table. So if you look at the open loop run with no data assimilation, and then you look at the scale of the assimilated data in terms of RMS error and bias, you can see that there's dramatic improvements, and then you see CMC as kind of a reference to see whether we're comparable to them. These graphs show snow depth versus time. And in this case, they're showing the RMS error over here and the bias over here. And there's CMC wasn't available for the entire time period. So some of the top ones are for the entire period from 79 to 2012, whereas the CMC period is from 98 to 2012, which is shown below. And I think the helpful point here is just seeing how the bias correction seems to sort of flatten out the behavior as expected, whereas there's a large seasonal bias in the open loop. Okay, so similar to the previous example, we wanted to, it's tough to evaluate against data when you're using the data to do the bias correction. It's a little incestuous. So the most robust way to evaluate the impact of snow assimilation is also looking at the stream flow data, because it's a completely independent measure. So in this example, it's the same exact analysis, the same 960-some basins, and if you look kind of at the summary, you have the stream flow metrics now, RMS error and bias in cubic meters per second over this entire period. And in this case, it's daily stream flow. And you can see we've got the open loop versus the assimilated, again, a nice reduction in the RMS error and a nice reduction in the bias. And you can see with the different lines, in this case, it's black is open loop and blue is with assimilation. Generally, you see improvement almost everywhere. And again, so that just suggests that there's value in the assimilation. So again, we can, this is kind of the last thing we're looking at right now. For the snow assimilation case, we decided that a relevant metric to look at would be the standardized runoff index, SRI, and we were just looking to see how the index would change with and without the assimilation. So we don't have a reference yet that we're trying to compare to in terms of drought-affected area. And I think some of the work on the task force related to metrics, and maybe Andy will talk about that, is, we can, it's difficult to define a reference, but if we can, then we can assess how we are either improving or degrading that reference. But this was the metric we chose, or the index we chose for the, to demonstrate the impact of snow assimilation. And you can see that clearly there's times where there's a big difference due to snow assimilation. So whether that would change the designation of drought, that would be up to, a given drought monitor author as to what's a significant change in a given area. This is, of course, averaged over CONUS. So over certain locations, similar to what we were showing for the southeast or the south, we could do, regional assessments of the impact. But overall, we think that there's, based on the analysis of stream flow impact, we believe that there's we're certainly improving stream flow, and we expect to be able to improve drought. So I guess time to summarize. So, you know, we've shown that it can improve the state variable itself, either in the case of the soil moisture essential climate variable assimilation, it improves surface and root zone soil moisture, mostly surface, and it also improves stream flow. And then we had another paper that I didn't discuss where we looked at evapotranspiration improvements. And I think the most important thing is that we're looking at how soil moisture assimilation could change the area in these critical thresholds, used heavily for diagnosing the severity of the drought. And so now we're moving on to looking at how the severity changes with time and how the soil moisture is affecting, you know, sort of the recovery part, as I showed you for the southeast. For snow depth assimilation, we know that we can improve snow depth and stream flow with that. We didn't really talk about another potential source of data, which is the snow-covered area data. We know that that helps in transition regions or for spring snowmelt, but in this example, we're focusing on the bias-corrected AMSR-E for the applications for drought. And similar to what I showed for soil moisture, we know that you can have a significant effect on a standard drought indicator, in this case, the surface runoff index. And that's it.
Great. Thanks a lot, Krista. Are there any questions here in the room for Krista?
Dan, did I hear her say that they've been equally successful with onset as well as termination of drought?
Come on up and ask, yeah. Sorry, Krista, Ken Mooney has a question for you.
Yes.
Krista, did I hear you say that you've been equally successful, define success however you want, with onset as well as termination of the drought?
No, actually, I think we hypothesized that we might be better at onset and recovery, but in the results I just showed for when you compare with the drought monitor areas, it looked like there was more potential for the recovery phase.
Oh, okay. Just the opposite of what I would have expected. Thank
you. Yes. So I can't. I think we still need to go into much more detail. I mean, even those regional results are probably a little too coarse to understand what's going on. So we're going to stratify them and dig into them a little bit deeper.
Great. Are there any questions on the phone line for Krista?
Yes.
Okay. Well, if there are no questions on the phone line, thanks a lot, Krista. We're going to move on to our next speaker, Amir Agakukchek. Amir, are you on the line?
Yes.
Okay, great. I'm going to try transferring control over to your computer now.
Okay. Can you see my slide?
Yeah, absolutely. So whenever you're ready, just get going.
All right. Good afternoon, everyone. Today I'm going to present an objective multi-index drought monitoring framework, something similar to U.S. Drought Monitor, but we're designing it such that it can be extended to global scale fairly easily. I'd like to acknowledge my co-authors, Zheng Chao Hao and Navid Nasri. So there are already a lot of indices out there. We don't necessarily want to develop a whole new index. Instead, we want to develop a framework to combine information from different indices. For example, here on the left, you see SPI, which is based on precipitation for January 2012. And on the right, you have soil moisture, SSI, standardized soil moisture index. Of course, they are not the same. We don't expect them to be the same. For example, soil moisture responds to precip with some delay. The question is, if you have multiple indices like this, how do you combine them together for an overall assessment of drought condition? And later on, I show that by combining information from different sources, there is a chance that we can improve drought onset detection. So here is an example of 2007 drought. If you focus on the southeastern U.S., on the left you have SPI for 4 consecutive months, and the same maps from soil moisture. These are based on NASA MERA data. They have the same scale as the U.S. Drought Monitor. For example, on the southeast, you see that in January 2007, both indices indicate abnormally dry, and then the drought develops. By April, FPI shows almost recovery, and it continues the recovery, but soil moisture shows persistence in drought. So if we only look at one metric, basically it could be quite misleading, and later on I will show you in this time series. Here, for example, you see time series of FPI and SSI for climate division 3 in California, 3 months at the top, 6 months and 12 months at the bottom. You can see there are differences, the ones that are highlighted with green boxes. You see there are differences between these indices, and in fact, in some cases, over several months, there are significant differences. Precipitation by nature is a lot more variable than soil moisture at longer scales, at least, and basically, you see a lot more variability from precipitation and soil moisture. And now our objective is to somehow combine the information into one overall assessment. We are using the concept of joint distribution or multivariate distribution to create a joint distribution function from multiple indices. We are right now working on MSDI, or Multivariate Standardized Drought Index, which is basically an extension of SPI. It has the same formulation, more or less. It is standardized, similar to SPI, but the difference is that the probability that is used into the inverse normal is based on joint distribution of 2 or more variables. For example, X could be precipitation and Y could be soil moisture. There are different ways to develop a joint distribution function. The result I am presenting is based on a non-parametric approach. We have tried also other parametric approaches. I can provide more details since I have only 15 minutes. I can provide more details about the methodology if you're interested later. Here is an example of how it works. This is, again, Climate Division 3 in California time series, data used from 1932 to 2010. I have zoomed into 1973 to 96 just for better visualization. If you look at, for example, this period, which we had a major drought in California, I have zoomed into this part right here, and you can see that SPI and MSDI both start at the same time, and soil moisture is this one, the dotted line. So soil moisture shows the start point, the onset of drought a little bit later, around a couple of months later. SPI detects earlier, that has been mentioned in the literature as well. So MSDI starts as early as precipitation, and then if you look at this period, SPI shows drought termination over here, while soil moisture shows drought termination a couple of months later. As you can see here, MSDI ends with soil moisture. So it starts as early as precipitation and ends based on soil moisture. And we know that basically soil moisture shows drought persistence better than precip, because basically precip is more variable. And in this period, basically, if you look carefully, in this period where we had a major drought, you can see that precip in 2 instances for 1 or 2 months, it shows even a very wet condition, but it is very temporary, again, because of high variability of precip. If you look at other cases, this is 1998 drought. Again, it's the same pattern. MSDI starts as early as SPI, ends with soil moisture. Another example, again, more or less the same. This is Climate Division 5. Now, let's look at U.S. Drought Monitor and these 3 indices that I've been introducing. Again, on the top you have a U.S. Drought Monitor, on the bottom left you have SPI, on the middle SSI, soil moisture base, and on the right you have MSDI. So here, for example, again, if you look at the southeast, again, SPI and SSI show abnormally dry. If you look at MSDI, it already shows almost E1, so a more severe condition. U.S. Drought Monitor also shows D0. And then later on, if you look at 4 months later, the same area develops into a major drought, an extreme drought condition. So based on the joint distribution function, if you have two different data sets here, precip and soil moisture, both indicating drought, like in this case, the joint distribution would lead to a smaller probability, which means slightly more severe drought condition. And we believe that could help with basically earlier detection, or at least an indication of an extreme drought coming up, as in this case, for example. And again, in this 4 months later, in April 2007, SPI almost shows recovery. Soil moisture still shows drought persistence. U.S. Drought Monitor also shows drought, and MSDI also shows drought persistence. And if you look at the Western U.S., I would argue that MSDI is in better agreement with U.S. Drought Monitor. Of course, as Krista mentioned, a lot more information goes to Drought Monitor, so this is not a fair comparison, but gives you an idea. In the 2012 drought, for example, this is April. Again, drought, and the SPI only shows drought in the southeast. Soil moisture shows drought in the west and also southeast. U.S. Drought Monitor also shows in the western U.S., a large portion of the western U.S., and you cannot see that from precipitation alone. Then MSDI, you see this is how it looks like. It is in better agreement again, but it is not, of course, perfectly matched with U.S. land. We looked at the probability of drought detection. Again, the reference is U.S. Drought Monitor. Here on the x-axis, you have months from January through August. This is the 2012 drought. If you look at only precipitation, this is the detectability of drought detection is around 40% to at most 60%. Soil moisture is slightly higher with respect to U.S. Drought Monitor. MSDI, the combination, is consistently higher. We have done this for different scales. This is the lower figure is 6-month scale, SPI, SSI, and MSDI. At 6-month scale, we expect the precip and soil moisture indices to be more consistent with each other as they are here, but still at 6-month scale, MSDI has a higher drought detectability. And we are making the data available on our website. There's drought.eng.uci.edu. Basically, let me switch to, can you see my desktop now?
Yeah, we can see that, the web browser.
All right, so basically the data is now available. This is still work in progress, but we are trying to make this as a data distribution system. For example, you can take the data set we have right now, MERA and GLDAS. For example, 2011, August, based on soil moisture, and you can look at precipitation, and also you can look at, for example, MSDI. These three are now built in, and the data is available. For example, this is 2010. You see the Russian heat wave and Russian drought very clearly here. We can move into 2011 Texas drought and also Horn of Africa. The data is also available on our FTP. If you click on download, you will see all three products, SPI, SSI, and MSDI. Again, this is a work in progress. We are adding some more elements to this system. Let me move forward. Okay, so for now we have this 3 indices based on MERA and GLDAS. We are working on 2 more data sets. One is a kind of near real-time satellite-based drought data set, which we combine real-time satellite observation, and we combine it with long-term GPCP. We get climatology from GPCP, and we have a Bayesian correction algorithm to make the climatology consistent. And that is almost ready, so it will be added to our website sometime this week. So that would give you kind of real-time monitoring. And we are also working on a kind of a short-term forecast based on CFS version 2. Our approach is, again, we are looking at the overlap between CFS and our real-time drought data, and we have recently developed a kind of Bayesian correction algorithm. We want to apply that to CFS. It is work in progress, but should be available soon, and that would provide 3 to 6 months forecast based on CFS, conditioned on near past satellite observations. And we are hoping to combine this information with a kind of land surface model calibrated with ECV, similar to what Krista presented, so that we combine the whole thing, the two products, as to one composite multi-index drought prediction, let's say, model, and that should be available hopefully in the next 2 or 3 months from now. Okay. That's it. Any questions?
Oh, great. Thanks a lot, Amir. Are there any questions in the room? Okay, I'm going to have to unmute the phone line, so everybody bear with me for a moment. All right, are there any questions on the phone line?
Yes, this is Rongfu.
Can everybody make sure that their phones are muted, unless you're wrong? Go ahead, Ron.
Yeah. How to get soil moisture index globally?
I'm sorry?
How do you get SSI globally?
Well, MERA is a global product, so it's a basically land surface. It's a model-based soil moisture data that is available globally. We have also used ECV, the one that Krista also mentioned. That's also available globally, but of course it has some gaps. So basically, that's also another option that we have tried, and we have the data too, but it is not on our website right now.
Okay, thank you.
This is Jared from NOAA. Yeah, my question is, when you computed the SSI, you just use the surface soil moisture retrieval from satellite?
No, the soil moisture is model-based. So it's coming out of NASA MERA data, MERA land data. So it's not pure satellite. It's it's a model-based, but the satellite data are used into that system.
You assimilated the satellite data, or just replace the top layer? How did you use the satellite data?
So again, I'm not modifying soil moisture data. I'm using just what's coming out of MERA land data. I believe that what they are doing, they are using satellite data, and I understand that they have recently started using ECV data basically to assimilate into MERA data, if I understand correctly. But they have also integrated other satellite data sets, including ANSERI, I think, into MERA land data.
Okay, thank you.
So I'm not doing any assimilation. I'm not changing the outputs of NASA MERA data at all.
Okay, thanks.
We have time for one more question. Anyone else?
Hello?
Yeah, hi.
Hi, this is Giuseppe Mascaro from ASU. I have one question. When you calculated the probability of detection, your observation was what, the U.S. Drought Monitor?
U.S. Drought Monitor, yes.
And so you...
We have graded U.S. Drought Monitor, and we have graded outputs. So basically, we used U.S. Drought Monitor as reference.
Okay, so you classified your MSDI
yes.
And as, okay, thank you.
Okay, great. Amir, thank you so much for the talk. Our next speaker is Andy Wood. Andy, are you on the line?
Yes, I am.
Okay, I'm going to try switching control over to your computer.
Okay, can everybody see my screen?
Not yet. So go to the view menu, or sorry, go to the share menu and then click My Desktop. Or go to the Quick Start tab and click the Share My Desktop button. Okay, great.
Okay, thanks. Okay, well, I just want to thank Dan and Anna Rita and others there for inviting me to present today. I want to talk a little bit about some activities.
Andy, I'm sorry to interrupt, but we're actually, here, your screen just came up, but we're seeing a Word document and now a Firefox window.
All right.
Okay, that's great. Yeah, we can see it now. So go ahead and get started. Sorry about that. Now we're back to Firefox.
Oh. Okay.
Okay, that looks good.
That's better?
Yep, yeah, we can see your slides.
Okay, I just wanted to talk today a little bit about some work that's gone on under the, in the context of the NOAA MAPP program Drought Task Force. And the talk in particular focuses on a framework which we've advocated to try to steer drought researchers toward assessing their results and analyzing various droughts case studies in a context that gives us a lot of insight into the science that's being supported through MAPP and other funding programs to advance our prediction and monitoring capabilities in drought. And at the start, I'd also like to say just a few words about the Drought Task Force itself. So an overview of my topics is to give a brief overview, summary on the MAPP Drought Task Force, and then just briefly outline this framework for drought science evaluation that we've worked on, and then give a short example of that, an application of that framework, and then a comment on future directions. So the MAPP Drought Task Force came about a little over a year ago to try to orchestrate and gain some synergies from the variety of different threads of drought research that were being supported by MAPP, and to ask questions about these efforts and how their success in advancing monitoring and prediction, not only scientifically but from an operational perspective. One of the main achievements of the task force was really to bring together different researchers in a venue that provided for discussion and exchange, and then as well as through these linkages to contribute to various other efforts within NIDAS and activities at NCEP, not to mention kind of coordinating with and leveraging other national and international efforts, such as the National Multi-Model Ensemble, and the linkage there has sort of promoted a broader expansion of products being developed and analyzed, and other international groups, such as through the WCRP. Some of the key activities of this task force over the last couple of years, as I mentioned, have been just enhancing this communication and coordination. For the most part, that's taken place through monthly telecons, and these have recently been given a structure in which they have narrative calls twice a year to assess the phenomena at work in current droughts of interest. A kind of research to capability type telecon twice a year, which will look at the kind of the movement of some of this research into operational activities, and then monthly science-oriented sessions, which comment on just a range of science issues being looked at within the different task force groups. There's also a wiki page that's mostly for internal use and a presence on the NIDAS web page through a drought task force linkage. And then, as I mentioned, there are links to the National Multi-Model effort. one of the other big activities has been, as Dan mentioned, organizing a special collection in Journal of Hydrometeorology on advancing drought monitoring prediction, and that seems to be going pretty well with a whole range of contributed papers. And then lastly, the group has kind of set up an infrastructure that I think serves as kind of a de facto test bed for looking at drought science. And that infrastructure centers on kind of three groups, one of which is a metrics group, one is the test cases, and one is focused more on drought early warning systems. These groups are led ably, I'd say, by Enrico Mariotti and Siegfried Schubert, and supported by not only researchers funded by MAPP, but also through other programs and agencies and partner organizations such as National Drought Mitigation Center and NIDAS. The metrics group in particular is, which I've been trying to lead, have about 6 people working within it to try to define metrics not of drought or of drought variables or drought status or state, but really metrics that help us assess the quality of the drought prediction and monitoring research and their advancement over the last decade or more through current science. The test cases group has focused on to find a number of key droughts in the last half century, the western U.S. drought, the southeast U.S. drought, and the current Tex-Mex drought, which would focus the activity and the analysis into some kind of common areas to help us get the most out of the different strains of research. And lastly, Kingsley Moe has been leading up this effort to try to synthesize some of these advances and or bring them to bear on operational drought monitoring. Within the metrics group, I just wanted to make clear that the Drought Task Force is, for the most part, focused on geophysical science. And so our questions, although there are a lot of aspects of drought that extend into social and economic impacts and ripple through various management systems, for the most part, we're looking at variables that we can measure, predict, monitor, and so forth, such as stream flow, precipitation, soil moisture, snow equivalent, temperature, ET, and potential evaporation. But we are also interested in assessing our research and capabilities in the areas that support decisions, and so things like the drought monitor categories and the seasonal drought outlook categories are of interest. So with that, I want to turn toward just outlining this framework for assessing drought research. And at the outset, I want to say that there's, for those familiar with verification and who have been doing research for a long time and assessing their own research, there is not a lot that is new here, but there are some key points to kind of emphasize. And those are, I think, the central ideas is that where we often evaluate our modeling or our predictions or our geophysical, simulation system, whatever it is, kind of overall, we really need to try to use performance measures that are specific to the drought phenomena and help us and to states that when the system is in drought, and help us gain insight into the various features at work. And also, and I'll give some examples to illustrate this. Also, we really do want to, because we're trying to measure the advance over some previous system or previous capability, we want to have an explicit inclusion of a benchmark capability or science that we're measuring against. And again, many of the talks earlier today have done this. And where possible, I think we want to try to focus on decision-relevant features of drought, such as key point or key features such as the onset or recovery or maximum severity that may be of interest to decision makers who have to set in place programs to respond to drought, et cetera. So basically, the framework components include whatever the new capability that's being assessed, is the definition of this benchmark capability, which could be operational or it could be a research capability. And where possible, you should try to avoid picking the easy benchmark, the climatology, where you really do have more information at hand. We'll need the verifying observations and some sort of analysis data set. In this case, it often consists of hindcasts or observational archives, such as with the USDM, that are relevant. And as with all research, there's an encouragement to document and pay attention to other work in the field. And I think this is also aligns with the general task force objective of creating more synergy and sharing between different researchers in the drought area. So with those sort of broad elements in place, some other considerations are that the assessment should really try to employ a skill score framework, which combines the new capability or science to the kind of reference capability. Again, it's not anything new really, but it's not always in place in the assessments we do, even in the context of drought research. Typically we'll need to think about drought thresholds, drought condition thresholds in ways that we might not have before. For instance, if we're just measuring the overall performance of a system, we may never have to decide when that system is in drought or what state might be most relevant for drought, but we're encouraging that here. And then again, highlight these features that are important for decision makers. So predictans and for a variable of interest, which could be stream flow, might be things like onset, recovery, drought condition, duration, and severity. I think we do want to look, and for those, we look at average lead time, average error, and some of the features of a drought prediction include things like changing skill over different lead times. We do want to look at some overall values, things like correlation of the system. I mean, that is of interest, as well as just these kind of metrics that are very specific to the drought condition, where we might use a Breyer skill score for probabilistic prediction, or critical success index, or equitable threat score, or as Amir showed, say, a probability of detection, that kind of are all metrics that are underpinned by the definition of a drought category. Just an example of an overall metric, for instance, not to pick on Kingsley Moe, but in a paper recently, they showed a very useful analysis of the error for soil moisture predictions for, I guess, lead 1 month forecast, and they compared to baselines, CFS version 2 versus CFS, well, I guess that's the observation, but NLDAS persistence versus the NLDAS ensemble, so there's nice use of baselines there. But this is kind of an overall performance, and when we have these skewed variables like precip, runoff, or snow, a lot of that performance may be dominated by non-drought errors, and that's true even for soil moisture. Here's one that's a little bit different. This is from the other Dr. Wood, Eric, and showing an analysis that focused on at least one part of the spectrum, the lower tertile of precipitation. These are forecasts with National Multimodal Ensemble. And, I like this because not only does it have a baseline such as ESP as the kind of benchmark, and the NMME is the operational capability, but it also focuses on, it highlights seasonality, and it focuses on sort of the dry end of the spectrum. That's not to say the dry end is the only end of interest. The wet end of the spectrum may relate to drought recovery. So the point is just that the analyses do get more to the phenomenon, or help get more to the phenomenon driving drought. Not sure how much time I have since I started late, but I'll try to go quickly through a few slides on an example. This example is the...
yeah, just a couple minutes, Andy.
Okay. U.S. seasonal water supply forecasts. In the western U.S., these forecasts are widely used and heavily influence the management of water, and not only in the southwest but in the northwest as well. Right now, the Weather Service makes two types of water supply predictions. They're typically for runoff volumes from snowmelt, which occur in April through July. The forecasts are made in January through July, and the two types are the ESP, an ensemble prediction, and the statistical water supply prediction, which is also gives uncertainty bounds. And MAPP is funding a researcher, Balaji Rajagopalan, among others, to look into whether these can be more objectively merged into a better water supply forecast. And here's just an example of some of the key areas in the upper Colorado where the forecasts are of interest for managing water. This is one of the locations where in a Hain cast over 30 years, you can see the kind of variation. The black are the observations, and the variation in the forecast from April 1 from the ESP, the SWS, and here's a multi-model based on generalized linear modeling. So in this case, just to go through the how this fits into the framework, our new capability is the sort of multi-model water supply forecast where you're going to use a Bayesian model average. And then our baselines are these existing ESP, SWS, and also just a simple average of the two, which would be the simplest possible multi-model. Verifying observations are observed naturalized runoff. And we have this Hain cast of 30 years for these forecasts that we can use to do the analysis. I'm just going to show the sort of overall water supply median correlation performance as well as Breyer scale associated with drought. Let's see. So just as an example of how these probabilistic forecasts look over time, this plot shows if I define drought for my Breyer score purposes as a 10th percentile flow. Climatological forecast of that flow is 10%, and or probability is 0.1, and the various forecasts such as the BMA, the ESP, the mean, and the SWS give different probabilities of drought in these different years, and the drought years are highlighted in gray. It does show that in general, this is a January 1 forecast very early in the year, snowpack's pretty low, that you have a slightly elevated probability of drought in some of the drought years, but you also have it in some others. By the time you get to April, you can see that these approaches are quite good at picking out drought years. ESP and BMA give almost 80% of drought by April 1. This is for runoff in April 1 through July. And then the SWS and the mean do less well, and the BMA is pretty close to the ESP. If we go and evaluate these sort of overall, pooling a number of upper Colorado locations just to get the sample sizes up, one of the things we see is that the kind of the overall performance looks better, particularly in the late of the year for the BMA. It's slightly better anyway than the ESP and the average, and a lot better than the SWS prediction. This is for March and April 1 forecast. But if we just look at that Breyer score, it kind of gives a slightly different picture. We're still the sort of improvement, which is positive values on the Breyer scale score, over SWS and average is notable. But it actually does worse in all months in the ESP, and it's not clear why that is. We haven't looked at it quite yet in enough detail, but I assume it's because these model combinations are trained on all the years in the sample, and they're not necessarily optimizing performance for the drought years. So the overall point of this example is just that looking at things through a kind of prism of drought event perspective gives a slightly different view that may be helpful or I think is really essential for us to assess these different capabilities that we're supporting through our research. I just want to make one comment on monitoring. obviously, verification scores have been, for decades, quite common for evaluating prediction, particularly for floods and extreme events. Drought is an extreme event, so it shouldn't be any different. What about drought monitoring? Drought, as everybody knows, is this multifaceted phenomenon that for which there is a lack of, in some ways, observations. And particularly we have had a concern that we can't really use something like a USDM or a drought monitor category as a verification for drought. But 2 points to make just are that I think the drought task force focus is really mostly about the science, and when we assess various parts of our science, such as land surface modeling or climate simulation or remote sensing, we're comparing them in a very standard way against physical measurements. And so this overall framework idea of trying to focus on drought phenomenon as opposed to only overall phenomenon and look at key drought features still applies, particularly to drought science that's physical. I think for these non-measured drought designations, such as D4, I think the idea of using the drought monitor has gained acceptance. It certainly has appeared in the 3 previous talks. And given that it's a synthesis, even if subjective, of many, many observational data sets, Mark Swoboda can talk about that when you catch him, I think it's perhaps been accepted as the best synthesis we have. And I wanted to point out, too, that the Drought Impact Reporter for very specific places and events has really grown to have a wealth of information. So with that, I just want to, I think I'll...
Great. Thanks a lot, Andy.
Well, I was just going to say, in summary, I'm just presenting this framework that is not made up of anything new, but overall just stresses some real key points focusing on these phenomenon. And then also that in the future, Drought Task Force will continue with some of the things that we described before.
Okay, I'd like to, thanks a lot, Andy. I'd like to leave time for just one quick question if there's anybody on the phone or in the room who has a question for Andy. Questions? Okay, well, I'd like to thank all 4 of our speakers today. This was an excellent webinar. You can see there's a lot of great research going on that's going to improve capabilities, which is just very encouraging. We have another webinar next month on the topic of drought. We're going to switch to drought prediction, and we'll have 4 speakers: Bradfield Lyon from the International Research Institute for Climate and Society, Kinsey Mo from the NOAA Climate Prediction Center, Eric Wood from Princeton University, and Siegfried Schubert from NASA Goddard. So thanks to everybody for joining today's webinar, and I hope that you'll be back next month.